This is our great pleasure to announce the next seminar of our research group on graphs, games, and other stuff. Our today's speaker is Niclas Boehmer, currently at TU Berlin, I hope. He will present a work about stable many-to-one matching with lower and upper quotas, which is actually a very nice paper that got the Best Student Paper Award at the Wine Conference 2020.
Okay, yeah.
Please.
Thanks for the introduction. Yeah, my name is Niclas Boehmer. I'm a PhD student from TU Berlin, and this is a joint work together with Klaus Heger, a colleague of mine, also a PhD student at TU Berlin. And yeah, as said, this was presented as last year's wine, so in last December, so it's a rather recent paper. And we are currently also working on a journal version, and there will be an archive update soon. So if you want to read the paper, then maybe wait for 1 or 2 more days, then there will be also an updated version available. Yeah, and yeah, please feel free to interrupt me at any time to ask questions. I'm not really sure about the background of people here, so I might be a little bit yeah, too detailed or too less detailed at some places. So yeah, just please interrupt me if anything is unclear. Okay, so the talk is about fine-grained view and stable many-to-one matching problems with lower and upper quotas. And I will start by introducing you to stable many-to-one matching problems. And afterwards, I will introduce lower and upper quotas into these stable many-to-one matching problems. And after that, tell you what our fine-grained view is and what results we obtained. And then we'll go into detail for 1 or 2 of these results. Okay, so let's start by defining the arguably most famous many-to-one matching problem, and this is the so-called hospital residence problem. Some of you might know the, let's say, a little bit more famous stable marriage problem, and the hospital residence problem is a generalization of this stable marriage problem. So we have, on the one side, we have some set of hospitals, on the other side, we have some set of residents, and we assume that we have M hospitals and N residents, and we want to find a matching of hospitals to residents, or residents to hospitals. And we assume that each hospital specifies a subset of acceptable residents. So each hospital tells us, okay, I would accept to be matched to this resident and this resident and this resident, but not the others, for example. And additionally, we require that each hospital gives us, in fact, a strict ranking, a strict preference order over the subset of acceptable residents. So we really know for each hospital, okay, this is the most preferred resident of the hospital, this is the second most preferred resident, and this is the third most preferred resident. And lastly, we are given an upper quota, which quantifies the number of residents that can be matched to each hospital. Symmetrically, we have for the residents also, each resident has strict preferences over a subset of acceptable hospitals. So again, a resident can specify a subset of hospitals it would like to be matched to, and then a strict preference order over this. And as said, the task is to find a matching M of residents to hospitals where we want the matching to be, first of all, feasible and then also stable. And for this, we need to define what stable and feasible means. For feasibility, we require that only residents in hospitals that accept each other are matched to each other. So we require that both of them need to be kind of, in principle, okay with being matched to each other. Then we require that each resident is matched at most once. So we allow each resident to only be part of one edge included in the matching. And on the other hand, we have the hospitals. The hospitals can be in principle part of multiple edges in the matching, can be matched to multiple residents, but we require that they are at most matched to upper quota many residents. So the number of residents matched to a hospital needs to be equal or below its upper quota. We now come to the definition of stability, and we define stability by the absence of so-called blocking pairs. A blocking pair consists out of a resident and a hospital, and the intuition behind the blocking pair is that a pair of RH is blocking if both the resident and the hospital somehow prefer being matched to each other to the current situation, where what the current situation is depends a little bit on whether you are a resident or a hospital. So for a hospital residence pair RH to be blocking, we first of all require that they need to accept each other. This is quite simple and quite plausible, I would say. And then we require that for the resident needs to be either unmatched in the current matching, which corresponds to kind of the resident's least preferred choice. So each resident prefers to be matched to someone from his acceptable subset of hospitals to being unmatched. Or alternatively, we require that the resident prefers H, so the hospital from the blocking pair, to her current partner. For the hospital, we either require that the hospital prefers R to one of the residents currently matched to the hospital. So this somehow means that the hospital would be willing to kick one of the residents currently assigned to it out of the matching to accommodate R instead, or that the hospital H is undersubscribed, where H is undersubscribed means that H has still free capacity left, so that below its upper quota, many residents are currently matched to the hospital, and we somehow assume that a hospital is always okay with accommodating more residents it accepts in stable matching. Okay, so far, this is everything on the definition of the hospital residence problem, so I hope this was kind of understandable. I will also now make an example. So here we have an instance, and we have here like 3 residents and 2 hospitals, and we assume that both hospitals have an upper quota of 2, and the preferences are encoded in these edges here. So we draw an edge between a resident and a hospital if both accept each other, and the preference relation here is encoded in the numbers closer to the agent. So for example, the first hospital prefers the first resident to the third resident to the second resident, which is encoded here like in the 1 and the 2 and in the 3. So this is kind of the ranking of the agent. And yeah, we want to find a feasible matching not admitting a blocking pair. And for example, this matching, this is not a stable matching because of the third resident and the second hospital. This is a blocking pair because the third resident prefers the second hospital to the first hospital, and the second hospital is undersubscribed because only one resident is matched to it. On the other hand, here now this is a stable matching, which can be actually easily seen here because each resident is matched to its most preferred hospital, which directly implies that this needs to be stable because no resident would want to be involved in a blocking pair. Okay, so now coming to the applications of this model, the probably most famous and also the one where this model has been most applied previously is probably assigning students to courses of studies at universities or to universities in general. So one can think of, we have the students on the one side and the courses of studies on the other side. And okay, students have obviously preference over courses of studies, but courses of studies might also have preference over students, for example, based on their average grade of their A levels or something like this. And also it's kind of natural to assume that most courses of studies have some upper bound, some limit on the number of students that can be enrolled in the course because of some practical, economical, logistical constraints. Other examples are assigning medical students to hospitals, so or more broadly speaking, kind of assigning career starters to their first workplace in a central fashion, or also when it comes to free time activities, assigning tennis players to coaches. So one can think of tennis players, they have preference over coaches. Each player only wants to be supervised by one coach, but one coach can supervise multiple players. So you again have this bipartition and may be interested in finding a stable and feasible matching. However, if you think a little bit about these applications, you may notice that also lower quotas naturally arise here. So a lower quota that needs to be met such that the hospital can open to accommodate the students. So for example, when it comes to courses of studies at universities, I mean, it's quite unlikely if in 1 year only 2 students enroll in some course of study that the university will actually offer the course, because it's maybe also practically infeasible because some works need to be carried out in groups or something like this. So it's kind of, in most of these applications, one can also think of lower quotas. So each hospital also has a lower quota, and the lower quota needs to be met such that the hospital can actually open to accommodate any students, and otherwise no students can be assigned to it. Okay, and this idea of lower quotas has been incorporated into the hospital residence problem in a previous paper that I will reference in the related work section that will come soon. But let's first of all introduce the model. We now speak of the hospital residence problem with lower and upper quotas. And the only thing that changed here now is that each hospital also has a lower quota. And when it comes to feasibility, the definition is still the same. However, now the crucial difference is that for a hospital, we either require that both the lower and upper quota needs to be respected. So the number of residents matched to it is either equal or above the lower quota, and below or equal to the upper quota, or the hospital needs to be closed. This means that no students or no residents at all are assigned to the hospital. For example, here, this matching encoded in the red arcs here is now, red edges is not a feasible matching because the second hospital has only one student assigned to it, but the lower quota of the hospital is 2, which means that, yeah, the lower quota is violated, and this is not feasible. For stability, we still require that no blocking pairs exist. The definition of a blocking pair remains completely the same as before. However, we also now require that no blocking coalition exists. And the blocking coalition, the idea behind this is that we want to prohibit the existence of a group of residents who are enough to open a currently closed hospital together and would also all prefer this to what they currently have. So somehow like opening a currently closed hospital. And formally, we say that a group of L residents in the hospital H form a blocking coalition in a matching M if L, so the number of residents, is equal to the lower quota of H, if H is closed in M, and if each resident prefers being matched to H to the current situation, which means that either each resident is either unmatched in M or prefers H to her current resident or to a current partner. So, for example, here now this is not a stable matching because there exists a blocking coalition consisting out of the first resident and the second resident. I mean, the second resident prefers the first hospital to the second hospital, and the first resident is unmatched, and this means that they together form a blocking coalition to open here now the first hospital. On the other hand, kind of the resulting matching is also not stable here because there exists a blocking pair between the third resident and the first hospital, because the third resident here is currently unmatched, and the first hospital prefers the third resident to the second resident and would be therefore willing to kick out the second resident in order to accommodate the third resident. So yeah, again, this is not stable. As people have before looked at, or the standard model is just upper quotas, and people have before looked at lower and upper quotas combined, we also considered the case with just lower quotas, so where we assume that we have no upper quotas, which means that if the hospital opens, it can accommodate all residents, so an infinite number of residents, basically. And yeah, so what changes here is now that the upper quotas, they disappeared. The definition of blocking pair, feasibility, and blocking coalition still remain completely the same. However, if you think a little bit about it, then you may notice that all hospitals are always undersubscribed because they have no upper quota. So they will always have free capacity left to accommodate additional residents, which immediately implies that the preferences of them become completely irrelevant, because preferences of hospitals don't matter for feasibility, because acceptability can be also encoded in the preference of the residents. They don't matter for a blocking pair, and an open hospital is now always willing to be part of an open hospital is now always willing to be part of a blocking pair, because the blocking pair, I mean, the hospital is always undersubscribed, so the hospital is always willing to accommodate more and more students, and this means that, yeah, the preferences just don't matter here anymore, so we can also simply omit them. So we arrive kind of at a situation where only the residents have preferences over hospitals, and the hospitals have a lower quota but no upper quota. And now, kind of motivated by this observation, it's kind of, there's a natural third model, and this is if we assume, oh no, so yeah, okay. For example, this here now is a stable matching. Yeah, because I mean, blocking pairs cannot exist because there exists no open hospital except the first one, and there is also no blocking coalition to open the second hospital here, because the second resident prefers the first hospital to the second hospital. Yeah, and as said, it's now also kind of unnatural to consider the case where we have one-sided preferences, so only the residents have preferences over hospitals, but the hospitals have a lower and an upper quota, which kind of results in the house allocation problem with lower and upper quota. So the house allocation problem is typically the name of the problem where we have kind of one-sided preferences, and yeah, the residents have preference over hospitals, but not the other way around. Currently, I mean, typically they are called applicants and houses in the house allocation problem. Okay, so we assume that we have lower and upper quotas, and that residents have preferences over hospitals. And again, feasibility, blocking pair, blocking coalition, the definitions remain the same as before, or the initially stated ones. However, you now have to note that for a blocking pair, I mean, for the blocking pair, we had kind of two alternatives for a hospital. Either the hospital is willing to kick out someone to accommodate the new resident, or the hospital is undersubscribed. However, now the hospitals are simply indifferent among all the residents, so they are never willing to kick someone out because they don't care. And this means that a blocking pair must now contain an undersubscribed hospital. Yeah, so this was basically everything on the 3 different models we looked at, or the 3 different problems. Any questions on that? Okay, otherwise I would now proceed with related work. So as I said, the hospital residence problem with lower and upper quotas, which we denote by HR-QUL, has been introduced not by us, but by a paper of Biró and others published in 2010 in Theoretical Computer Science. And they proved that in contrast to the standard hospital residence problem with just upper quotas, stable matching may fail to exist here. And that deciding its existence is actually an NP-hard task, even if all hospitals have lower quota at most 3. So if the lower quota of a hospital is either 1, 2, or 3. After that, there has been some follow-up work, for example, a paper by Agoston and others who proposed an ILP formulation of the task of deciding the existence and actually constructing a stable matching in such an instance. And they also proposed some pre-processing steps and to decide which hospitals to open and which ones to close, and tested them experimentally. And also some authors kind of picked up the idea of lower and upper quotas and applied them in a different way. So for example, there's a paper by Hamad and others who proposed an alternative model where hospitals cannot be closed. So where for each hospital, in each matching, we need to match between its lower and upper quota many residents to it, and there is simply no possibility to close it. However, this gives rise to kind of quite different questions when it comes from from a computational complexity perspective. And lastly, the House allocation problem with lower and upper quotas has been considered by some authors before. However, they only searched for Pareto-optimal matchings, which is kind of the standard thing to do in the context of House allocation. So for hospital residence problem, we are usually interested in finding a stable matching. For House allocation problem, we are typically interested in finding a Pareto-optimal matching. However, the notions of stability and Pareto-optimality do not coincide here anymore if we restrict or if we impose the lower quotas, which means that, yeah, it's still interesting to look at stable matchings here, and no one has done it before, so we are kind of the first to do it here. And before I will now go over to presenting our results, a very brief reminder, recap of parameterized complexity of those of you who are not working on it on a day-to-day basis. So parameterized complexity is a framework to analyze the influence of a parameter on the computational complexity of a problem. If we have some computational problem and some parameter k, then there exists a variety of different complexity classes where this problem parameterized by this parameter or this number k could lie in. One of them is xp, where we say that a problem is in xp if there exists an algorithm running in n, which is now the size of the instance, to the power of some computational function in the parameter. So the computational function can be, or the computable function can be kind of arbitrarily, involving some exponents or something like this. And what is special here about this is this implies, or this an algorithm with this running time has a polynomial running time if we assume that the parameter is a constant. On the other hand, there also exists the notion of para-NP hardness, and we say that the problem is para-NP hard if it's NP hard already for a constant value of k, so already for, let's say, k equals 3, for example. And yeah, this implies that, so if we assume that p unequal np, then the problem that is para-NP hard cannot lie in xp, obviously. There also exists a more fine-grained view. For example, the complexity class FPT, or fixed parameter tractability. And we say that a problem is fixed parameter tractable if there exists an algorithm running in this running time, so some computable function in k times some polynomial in n. And again, what is kind of particularly interesting about this is we now have the bad part of the running time only scales or only depends on the parameter, which gives hope that for such algorithms, even for small k, that even for larger instance sizes, the problem still remains kind of practically solvable. And there also exists a notion of hardness, or even a whole hierarchy of hardness complexity classes when it comes to like fixed parameter tractability. The most basic or the most important one is the notion of W1 hardness. And yeah, the only thing that you basically need to know about W1 hardness at the moment is that under standard complexity theoretical assumptions, an algorithm, a problem that is W1 hard is unlike to admit an FPT algorithm. And W1 hardness can be established by parameterized reduction of a known W1 hard problem to our problem where, yeah, the details are not really important here at the moment. Okay, so let's now come to an overview of our results. We now here have our three different problems or three different models as the rows. So here we have the hospital residence problem with lower and upper quotas, here just with lower quotas, and here we have the house allocation with lower and upper quotas. And we now looked at, yeah, kind of, you can already see a bunch of different parameters and questions. The first parameter, or the first question that we looked at is what happens if the maximum lower quota of a hospital is at most 3. So kind of, yeah, picking up on this NP completeness result from Biró results that I already mentioned. So it was already known that the hospital residence problem with lower and upper quotas, that this is NP hard or respectively NP complete, even if the lower quotas of hospitals are at most 3. And we also were able to prove that this still holds for the other 2, or that this, like using an alternative reduction, we were able to prove that this also holds for the other 2 questions. Then it was kind of obvious to consider the case, what happens if the lower quotas of each hospital is at most 2. And here, this result kind of is the by far most involved one in our paper. So I think it's like a 6-page algorithm and a 14-page proof. So it's yeah, far from trivial to prove that actually if the lower quota of hospitals are at most 2, then the 2 hospital residence problem that we looked at are solvable in polynomial time. And in contrast to this, for the house allocation problem, we were able to prove NP completeness. Then we turned kind of to a related question, a more refined question. And that is, I mean, one can think of constructing a stable matching here as a 2-step process. First of all, decide which hospitals to open, and then assign the residents to the open hospitals. And now we ask the question, what happens if this first step, deciding which hospitals to open, has been already done for us? So the question, given some subset of hospitals, H open, decide whether there exists a stable matching, opening exactly the hospitals from H open. And for the 2 hospital residence problems, it's, yeah, we constructed for both of them a quite simple polynomial-time algorithm. For the house allocation problem, unfortunately, also this problem is NP complete. Note that this is particularly interesting because, again, in contrast to the standard hospital residence problem with just upper quotas, there might exist for all 3 models, there might exist stable matchings, different stable matching opening a different set of hospitals. So it might be the case that there exists one matching opening, let's say hospital 1 and 2, and one matching opening hospitals 2, 3, 4. So yeah, different stable matchings might open a different set of hospitals and even sets of different sizes. Now we come to, yeah, let's say quite obvious parameters of our problem. So the first one is the number of residents, N, and we proved here that yeah, the problem of deciding the existence of a stable matching is for all 3 models is W1 hard, which was actually, I mean, we did not really expect this because we somehow felt that with a bounded number of residents, we cannot express this much anymore. And that's why I will always, in the following, give you a brief overview of this reduction, because I think it's kind of, at least on the first glance, if you think a little bit about it, you would maybe suspect that it is fixed parameter tractable and not that it's W1 hard. On the other hand, I mean, if we look at the number of residents, then we also have to look at the number of hospitals. And they are proof that the problem, or all 3 problems, are fixed parameter tractable. Actually, one of, or at least the results for the 2 hospital residence problems, you can easily see why this is the case. And it's because of this polynomial time result, because we can simply iterate over all subsets of hospitals and ask, does there exist a stable matching opening exactly this subset of hospitals? And then, or yeah, for this, we invoke simply this polynomial time algorithm from here. So yeah, these 2 FPT results are quite simple. This one is also not super complicated. It's just an ILP-based result, so it's possible to bound the number of different residence types in the number of hospitals, and thereby construct an ILP with a bounded number of different variables, and then invoke the famous result by Lenstra. As the next step, I mean, you can think of, we have kind of two different types of hospitals. The first one are those which have a non-unit lower quota, so which need at least 2 residents to open. And the other ones are those that only need 1 resident to open. So you can somewhat distinguish between hospitals that effectively have some lower quota, which means a lower quota of 2, and those who are also willing to just accommodate 1 resident, which means the number of hospitals with a unit lower quota. And one could argue that one could expect that maybe only these hospitals with a lower quota of 2 make the problem complicated, or only those make the problem hard. And that's why we also looked at the number of hospitals with a non-unit lower quota, and our FPT results here kind of still easily extended. However, for the house allocation problem, this ILP bounded number of residence type approach does not longer work at all. And we were even able to prove that the problem is para-NP hard just for 3 hospitals with a non-unit lower quota.
Pardon me. So, but this is not the same. Like hospital with quota 1 is still something different than a hospital with quota 0, isn't it? Like, if I don't have assigned anyone to this, then it's closed in one model, and in the other one, it still counts like a destination of some blocking pair, doesn't it?
Yes, but a blocking pair is an equivalent to a blocking coalition to open this hospital. So it's kind of, it does not really, I mean, it makes different in the formal sense, but effectively it results in the completely same model. The same matchings will be stable or unstable.
Okay, thanks.
And yeah, so with either a unit or a 0 lower quota, this is kind of the original hospitals from the hospital residence form with just upper quotas. And yeah, so, and lastly, we considered, because one can also think of maybe opening a hospital comes at a certain cost, or closing a hospital comes at a certain cost. One may also be interested in finding a stable matching where exactly a given number of hospitals is open. So we considered the parameterized complexity of, given some number M open, decide whether they exist, a stable matching opening exactly M open hospitals parameterized by this number M open, or kind of symmetrically by the number of closed hospitals in the requested stable matching. And yeah, all our problems become W1 hard in this case. And for the house allocation problem, for the parameter M open, we were even able to prove para-NP hardness for, again, only 3. Even if we only request that 3 hospitals are open. Note that this W1 hardness, so this is not kind of an asymmetric result, because we don't know whether this is tight. So we don't have an XP algorithm for this case. So it could very much well be the case that this is also para-NP hard. However, except from this result, all the other W1 hardness, so all the other 3 W1 hardness results are also tight. So for them, we also have kind of simple XP algorithms. Okay, so what does this, or what should you take away from this kind of large table? And we believe that we have kind of at least 2 very interesting takeaways. And the first one being that the hospital residence problem with lower and upper quotas and the hospital residence problem with just lower quotas, that they are complexity-wise very similar. So for all of the questions we considered, they fall into the same considered complexity class. And even some of the algorithms, or I mean, the algorithms were kind of very similar, and the hardness results were the same, because I mean, hardness for the just lower quotas case also implied hardness for the lower and upper quotas case. And this, may be kind of interesting, because it tells you that upper quotas are not interesting, or that they don't really make the problem more complicated. So by adding upper quotas to the setting to just lower quotas, we don't really make the problem more complicated. On the other hand, the house allocation problem with lower and upper quotas is computationally more demanding than the other 2. For example, I mean, here we have the 2 polynomial-time results where we have NP completeness on this side, and here we have an FPT result where we have para hardness, for example. And on a high level, or like generally speaking, why this is the case is because the preferences of hospitals, they may act as a tiebreaker to decide which residents deserve kind of a good spot in a stable matching. So for example, one could think of, okay, we have one very popular hospital where every resident really wants to be matched to, and this popular hospital has an upper quota. And then we basically don't know anything about which residents are matched to this popular hospital in a stable matching, because I mean, we would simply need to iterate over all possible subsets of residents of the size of the upper quota. So yeah, it's using kind of this idea or this approach, one can easily encode hard problems into the House allocation problem with lower and upper quotas. And looking at the two hospital residence models, so lower and upper quotas and just lower quotas, the difficult part here is really to decide which hospitals to open. I mean, this is kind of directly suggested by this result. So if the question is, given some subset of hospitals, decide whether there exists a stable matching opening exactly the subset, this is polynomial-time solvable, which means that kind of the hard part is not to assign the residents to the open hospitals in a stable way, but to decide which hospitals to open. And we even obtained kind of, a little, or we even justified this kind of in a different way, because our hardness results, so for example, this W1 hardness result and also this NP completeness result, they also hold if you don't care about blocking pairs. So even if we only search for a matching which does not admit a blocking coalition, then the problem still remains hard. So it's really not about assigning the residents to the open hospitals or at all to the hospitals such that no blocking pairs exist, but it's about, or the complexity really lies in this blocking coalitions part. So in this, which hospitals to open, which hospitals to close, and somehow prevent the existence of coalitions that want to open a currently closed hospital together. And lastly, I mean, this is not such a surprising, and I would say a rather standard observation, is that our tractability results are quite volatile, in the sense that, okay, we have this NP completeness result for lower quota 3, but polynomial-time solvability for lower quota 2. Or for example, here we have FPT algorithm for just the number of hospitals, but para-NP hardness for the number of hospitals with non-unit lower quota. So if you have some tractability result, then it's, in this context, they don't necessarily extend to any broader problem or a smaller parameter. And in the following, and I want to present to you this reduction, this W1 hardness reduction for the number of residents. And the reduction is from multicolored independent set. So we are given a graph where each vertex is colored in one of k colors. And the question is whether there exists an independent set of size k, which contains exactly one vertex of each color. So for example, here now 1, 5 would be a solution here, because, I mean, this is an independent set and it contains one blue vertex and one green vertex. On the other hand, 1, 2 would not be a solution because we don't have a vertex of the green color and 2 vertices of the blue color here. And given such an instance, and I will use this example instance here, I now want to construct an instance of the hospital residence problem with just lower quotas, so we won't make use of the upper quotas here. And note that the multicolored independent set is W1 hard parameterized by the number of colors, respectively the size of the solution. So we will kind of exploit this by to prove that our problem is also W1 hard for the number of residents. And the construction works as follows. First of all, for each vertex, we add a vertex hospital with lower quota 2. So we have, I mean, for vertex 1, we introduce vertex hospital H1, for vertex 2, H2, and so on. Then we introduce for each edge an edge hospital with lower quota 4. So for the edge 1,3, we introduce the edge hospital H13. For 1,4, we introduce H14, and so on. And now we come to the, let's say, complicated part of the construction. And these are the residents and their preferences. So for each color, we add 2 residents. So we have, for the color blue, we have the resident R1 blue and R2 blue. And for green, we have R1 green and R2 green here in our example. And both of the residents, so one of them for each color ranks all vertex hospitals from this color in some arbitrary ordering, and the other one in the reversed order, where we at the moment don't care about the edge hospitals. So ignore the edge hospitals for the moment. So for example, here now the first blue blue resident ranks first H1, then H2. The second one ranks them in opposite order, so first H2, then H1. For the green color, the first resident ranks first H3, then H4, then H5, and the second one again in opposite order, first H5, then H4, then H3. And both color residents rank before each vertex hospitals all edge hospitals involving the corresponding vertex. So for example, before the hospital corresponding to vertex 1, we rank all hospitals corresponding to edges involving vertex 1 in some arbitrary ordering, which is in this case, okay, 1 is incident to 3 and 4, so we rank before H1 the hospitals H1, 3, and H1, 4. And yeah, this is kind of how the construction works. And then lastly, for each color, we add a penalizing component that enforces that one vertex hospital of this color needs to be open. And actually, this tells us already a lot more about how a solution to the problem may look like, because each vertex hospital occurs only on the preferences of two residents. The two residents corresponding to the color of the vertex hospital. So yeah, for example, H1 is blue, so it only appears in the preference of the two blue residents. And note further that each vertex hospital has a lower quota of 2. And this means, because we need to open at least one hospital, at least one vertex hospital for each color, that also exactly one vertex hospital for each color is open, because the number of residents simply do not suffice to open more than one vertex hospital for each color. And also that all edge hospitals need to be closed. So the edge hospitals, we simply don't have any residents to open them. And thereby, we kind of have directly a selection of vertices encoded in which vertex hospitals are open. So we know for each color, one vertex hospital needs to be open. So we directly have our selection of one vertex from each color in our open vertex hospitals. And now let's look at an example here. So for example, our selection of the vertices 1 and 5 would correspond to opening hospitals H1 and H5. So assigning the two blue residents to H1 and the two green residents to H5. And now to check whether this is stable, one has to note that for each color, the only hospitals both residents for this color prefer to the vertex, to the hospital to which they are currently matched, are the edge hospitals involving the corresponding vertex. So, for the first blue one and the second blue one, the only hospitals both of them prefer to H1 is H1, 3 and H1, 4. So the edge hospitals corresponding to the edges incident to vertex 1. And similarly, for the green color, the only hospitals both residents prefer to H5 is the edge hospital H25. Yeah, because here you can see it. And this here now directly says, by noting that each edge hospital has a lower quota of 4, and that each edge hospital only exactly occurs in the preferences of exactly 4 residents, because it's only the residents of the color of the two endpoints. We know that kind of all the residents, all these 4 color residents would need to be on board to open the edge hospital. And because here now we don't have an edge between 1 and 5, this implies that we don't have such a blocking coalition here. And you can also directly check this. So for example, for the edge H1, 3, these 3 residents would prefer this to what they currently have, but the last one does not. And symmetrically, so now assume that we have like an H1 and H4, or we want to select vertex 1 and vertex 4. And we construct the corresponding matching. This is now not stable because we have this edge between 1 and 4, which implies that all this implies that both residents of the blue color prefer this edge hospital to the vertex hospital they're currently matched to, and also the residents of the green color. So you can easily check here now that we have for the edge hospital 1, 4, all 4 of them prefer this to what they currently have, and thereby this is not a stable matching because this is now a blocking coalition. I hope this gave you somehow an intuition why the problem is complicated. This first of all proves, among others, NP hardness, even if each hospital has a lower quota of at most 4. And it also proves that the problem is W1 hard parameterized by the number n of residents, because the only thing that we did here is we introduced 4 residents for each color, and I think 3 more here in the penalizing component. So we introduced 7 residents we only introduced 2 residents for each color here and 3 here. So overall only 5 residents for each color. And because we know that a multicolored independent set is W100 parameterized by the number of colors, we also have kind of the hardness result for the number of residents here. Any questions on that? Otherwise, I'm very closely to the end. The only thing I want to mention before kind of wrapping up is why you may want to be interested in reading our paper to look up or to learn more about this polynomial time result for lower quota at most 2. So this question was already posed as an open question by the authors initially introducing this problem, so by Biró and others. As said, for lower quota at 3, they proved NP hardness, but the case lower quota at most 2 is hard. And why this is particularly interesting is because similar cases for closely related problems, for example, the hospital residence problem with couples, are known to be NP hard. So in other situations, you sometimes have, okay, we have a pair and they want to be matched to one thing. So we want to match pairs to one agent, which somehow felt to be similar. They are known to be NP hard. And that's why we also, I think, for the first, so this was the first question we kind of thought about when starting this project. And we thought, I think, about 2 or 3 weeks about NP hardness, so kind of really intensely. And we had multiple approaches where we thought, okay, maybe this may work, but they all in the end broke down due to something. And then after 3 weeks, we decided, okay, we think it's hard, but we are at the moment not able to prove hardness. Let's think about polynomial time solvability, which we somehow felt to be a little bit absurd in at that time. But then we, after some work, we were able to construct a polynomial time algorithm. And the algorithm is inspired by Irving's algorithm for stable roommates. So in the stable roommates problem, this is kind of, we have given a set of agents, they have preference over each other, and we want to find a matching of agents, but a one-to-one matching in this case. And we again want to find a stable matching, which means that no agent pair that both prefer each other to their current partner exists. So it's kind of a related problem, but not that closely related. So we somehow looked at this algorithm for stable roommates, and it works in 2 phases. And we looked at, okay, where do the 2 phases break down here? And both of them break down almost immediately. And then we kind of tried to extend them. So our algorithm still works in these 2 phases, and the ideas of the 2 phases are still very similar. So the first phase is kind of such a proposed and reject approach, similar to Gale's and Shapley's algorithm for stable marriage. And the second phase is kind of identifying a substructure, which is called rotations, and eliminating them. And we still do that, but both of them become kind of a lot more complicated. So the protocol for the first phase is a lot more complicated. In the second phase, the original definition of a rotation is quite clean, and we still try to cap this intuition, but I think we now have like 7 case distinctions about things that can happen. So it's not such a clean and beautiful algorithm. That's why it's also, I think, kind of infeasible to present it in such a short talk. But if you want to know or want to learn about how one may want to be able to extend such an algorithm for stable roommates to other stable many-to-one matching problems, then you might be interested in checking out our algorithm. So to sum up, what have we done is we have conducted a detailed parameterized analysis of the computational complexity of the hospital residence problem with lower and upper quotas and 2 close to related problems. And we believe that we somehow at least tried to identify the difficult parts of the problem and that we learned something about the problems. We also kind of proposed or constructed this polynomial time algorithm for, let's say, the natural special case of lower quota at most 2. And for future work, things that one could look at is, first of all, one could try to adapt our algorithm to other stable many-to-one matching problems. The most obvious one is probably one can also think of, okay, we now only have hospitals and we allow hospitals to be matched to hospitals. So each hospital has a lower and upper quota, so they still have lower upper quotas and or can be closed. And the task is to find a matching of hospitals to hospitals, where each hospital, as said, can be either involved in between lower and upper quota many pairs or needs to be closed, such that this matching of hospitals to hospitals is again stable. And yeah, stability is still defined in a very similar way. This is also known as the capacitated stable roommates problem because, yeah, you don't have this bipartition anymore. This is why it's called a variant of the stable roommates problem. And we think that our algorithm might be able to, extend to our algorithm, but it's at least not obvious to us at the moment. And lastly, we hope that our work kind of motivated others to conduct similar parameterized analysis of other hard stable matching problems because, yeah, we thought that we really learned something about the problem and hope that this motivates others to also learn something more about other stable matching problems. Thanks for your attention, and I'm now happy to answer questions.
Right. Many thanks. So we should unmute and thank you. Okay. Are there any questions?
Let me start with a simple question. Like you were speaking about this penalizing component, and it's just 3 agents or like 3 residents. Is it easy to present, or is?
And not without a whiteboard, or okay. It's actually I noticed it's 4 residents, and it's kind of very basic. So you can construct an instance with 3 residents and 2 hospitals that does not admit a stable matching. This was also presented. It's a very standard one, very standard construction, and then you can add an additional resident, which if matched to one of these 2 hospitals, then there can exist a stable matching. But if it's matched kind of outside of the penalizing component, then immediately no stable matching can exist. And kind of by this matching outside, we said that if kind of other hospitals that we don't want to be open are open, then immediately this resident would match to them and thereby outside the penalizing component, and then no stable matching exists. So yeah, it's not so complicated, but it's a little bit.
But my feeling was that you want at least one hospital being open, don't you?
Yes. Oh yeah. Good point. Yes, sorry. We had for the different reductions. We had a lot of different penalizing components, and they all work very similar. But yes, you're right. Yeah, but I think I'm now also not able to remember how exactly.
Okay, fine.
But it's not anything. It's no magic behind it. So it's a rather simple one, and you can, I think, come up with it in like half an hour at most.
Okay, thanks.
Okay, any other questions? Maybe
do the preference of the hospital is not come into play for the reduction?
No. All our, or at least, actually, all our reductions don't utilize preference of hospitals at all. Because, I mean, we had the reductions, if all our hardness reductions for the lower and upper quotas case actually only used the lower quotas. So we only use lower quotas, and thereby the preferences of hospitals are completely irrelevant. And then we had some separate reductions for the house allocation problem, but there we also don't have preference of hospitals. So I think none of our hardness reductions used any kind of preferences of hospitals.
Okay.
Let me give one more question. So, I mean, you limited the lower quota. Would it become easy if I limited the upper quota?
No. So most of our reductions also work for tight quotas. Okay. So even if the lower quota, so we also thought about, okay, let's parameterize maybe the problem by the difference between the lower and upper quota or something like this of the hospitals, but this doesn't help at all. Even stronger, most of our reductions even work if the number of residents that accept each hospital is exactly the same as the lower quota. So even if we already know exactly if the hospital is open, then those residents need to be matched to the hospital. Even then, we know kind of that the problem is still hard.
Okay.
Okay.
Interesting. Thanks.
Very interesting. Yes, I was about to ask for this tightness parameter because sounded natural somewhat. Maybe let me ask one more thing. I mean, Irving can actually extend his algorithm to even provide like like a characterization of all of the stable outcomes. Have you thought about this, or?
Yeah, no, I think we are not able to do this in this case. So we are able. I mean, the algorithm also gives us some stable matching.
Yep.
And actually, we know that each stable matching matches the same set of residents and opens the same number of hospitals, but not the same set of hospitals. So we kind of learn something from the algorithm, but we don't have any form of characterization. And yeah, what makes our algorithm also different is that Irving's algorithm applies the two phases kind of one after each other. So first once the first phase and then once the second phase, and we do it kind of interleavingly. So we eliminate rotations, then we do propose reject again, then we eliminate again some rotations, and thereby kind of it's, yeah, we don't have any kind of characterization that we could obtain from that because it's just not overseeable what happens, kind of.
Yeah, that was just a feeling that you were speaking about the rotations and there. I mean, in this Irving paper, there's this singleton rotations and this dual pair rotations, and then you have the characterization. So I was sort of afraid that nothing like this holds if you have like 7 case distinctions inside your definition. Yeah. Anyway, are there any other questions? Seems not to be the case, so we shall thank Niclas once again.
Thank you.
And that's the end. Thank you, Niclas.